Now, in the previous lecture, we discussed the homomorphism. So, what is the homomorphism? If there is some group G, so this is group G, and this group is G dash, and phi is some mapping from G to G dash. This is some mapping from G to G dash, and this is a G with binary composition if multiplication, and this is a G with binary composition again multiplication. So what we get this point if A, this point is B. So what is the image of this A, which is a phi A, and this point which is a phi B? So image of B point. Now homomorphism mean phi of AB, which is equal to phi A and phi B into phi B. So this is a for every AB belongs to G. So this mapping is called a homomorphism. So this is very important mapping, homomorphism. So remember this homomorphism. Now, if it is a homomorphism, so homomorphism depend upon the binary compositions, on the binary composition. Now, if it at this side the binary composition is with plus, and here it is a binary composition G dash into multiplication, then it will become phi of A plus B, which is equal to phi A plus phi B. This is of this kind. If here it is a of red color, here it is binary composition multiplication, and here binary composition is a addition. So this will become phi of AB, which is equal to phi A plus phi B. So this is a definition of homomorphism. So it depends upon the binary composition. So remember that this is a definition of binary homomorphism. If phi is also onto, then it is called a epimorphism. Epimorphism. So if it is homomorphism and onto, so this is called a epimorphism. If it is a homomorphism plus it is a 1 so this is called monomorphism. So in that case it is called monomorphism. So in the case of monomorphism, it is 1 as well as onto. It is only monomorphism if it is a 1 as well as homomorphism. If it is one homomorphism and 1 so 1 and onto, so this is a called isomorphism. So in that case it is called a isomorphism. If group are same, means G and G dash are equal. If group are same, in that case isomorphism is called a automorphism. Automorphism. And if group are same, then homomorphism is called endomorphism. So this is a endomorphism. So remember these definitions, right? Now after that, next definition is kernel of homomorphism. So next definition, which is called kernel of homomorphism. Homomorphism. So this is my next definitions. Now what is the statement? Now statement is let phi from G to G dash homomorphism and any set which is called kernel of phi. So this is a set of all x belongs to G, all element of G, such that its image is equal to identity of G dash. So this is called kernel of phi. So this is called kernel of homomorphism या kernel of a phi, where E dash, so remember that E dash is a identity of G dash. So this is the identity of G dash. For example, if I take of this kind, if I have, this is a group G and this is a group G dash, and this mapping phi from G to G, which is a homomorphism. So kernel of F are those points whose image is equal to E dash. So जिन्हां दा image identity ਦੇ ਬਰਾਬਰ ਆ ਜਾਂਦਾ ਉਹਨਾਂ ਨੂੰ ਅਸੀਂ ਕੀ ਕਹਿੰਦੇ ਆ kernel of F, kernel of phi. Now after that, the first theorem, that is the property of homomorphism. So what is the statement of the theorems? So what is statement of the theorems? So I take let phi from group G to G dash, this mapping be a homomorphism. This mapping is a homomorphism. So also remember the statement. So first part is number 1, image of identity which is equal to E dash. So basically it is a property of homomorphism. So first property is image of homomorphism is image of identity under homomorphism is again identity. Property number 2, which is a phi of x inverse. So image of x inverse which is equal to phi x raised to power -1 for every x belongs to G. And property number 3, so which is equal to kernel of phi, this kernel of phi which is a normal subgroup of group G. So it is a normal subgroup of group G. So that is my statement. That is our first theorem. Now first part is image of identity is equal to E dash. Now solution of this, if solution of this, I am going to prove the first part. So what is the first part? So image of identity is equal to E dash. Since G is a group, and E is identity of G, so it means E into E is equal to identity. This means this is my first step. it implies, so just see the steps. It implies phi of E into E, which is equal to E, this values. Now what is phi? Phi is homomorphism. If phi is homomorphism, it implies phi E. So this is again phi E, sorry. So phi E into phi E, which is equal to phi of E. So this value. So this phi E can be written as phi E into E dash. Why it is E dash? E dash because phi E is the element of G dash. So this can be written as this element is equal to identity of G dash. So since, so that's why, because since phi E belongs to G dash and G dash is a group, so phi E into E dash, which is equal to phi E. So that is the property of identity of G dash. Now from this, since again all the member are of G dash, so it means phi E into phi E, which is equal to phi E into E dash, right? So since G dash is a group, and under group it hold cancellation law. If it hold cancellation law, so it implies phi of E is equal to E dash. So this is by cancellation law. So why it is applicable? It is applicable because G dash is a group. So this is the proof of first part. Now second part again. So what is the second part? So second part is phi x. Now we know that since G is a group and group has inverse element, so it means x into x inverse, which is identity, which is equal to x inverse into x. Now it implies taking phi map on both sides. So phi of x into x inverse. So this is equal to phi of E, and again this is equal to phi of x inverse into x. Now since phi is homomorphism, so this can be written as fx phi x into phi of x inverse, and this value is equal to E dash. This is by property number 1. Again this value, which is phi is homomorphism, x inverse into phi x. So this values. So this is by property number 1. So since phi is a homomorphism. So right here why this is possible. Since phi from G to G dash, it is a homomorphism. Homomorphism. So now this value. Now if the product of two elements is equal to identity, then they are inverse to each other. If they are inverse to each other, then inverse of this element is equal to phi of x inverse, because they are inverse to each other. So it inverse is this element and it inverse is this element. So it prove the result number 2. Now after that, the property number 3. So what is this? Kernel of phi is a normal subgroup. So what is kernel of phi? Phi is a homomorphism. So this is a set x belongs to G such that phi of x is equal to identity E dash. So this is the identity of group G. Now First, it should be non-empty. Why it should be non-empty? Because I would like to take one element from this set. If it is a non-empty, then I can take element from this set. So since by property number 1, since phi is homomorphism, phi of E is equal to E dash, then it implies it satisfies this condition. E belongs to kernel of phi. So if E belongs to kernel of phi, then it implies kernel of phi is non-empty. Now it is a non-empty. Now I can take element from this set. So because I would like to prove it is a subgroup, then normal subgroup. So I take two element AB belongs to kernel of phi. So by definition of kernel of phi, phi of A is equal to E dash and phi of B is equal to E dash. So to prove it is a subgroup, I want to show that AB inverse belongs to this set. So AB inverse belongs to this set if phi of AB inverse is equal to identity. Now I take phi of AB inverse, these values. Now what is phi? Phi is homomorphism. So this can be written as phi A into phi B inverse, these values. Now what is this? It implies phi A. Now what is phi B inverse? This is phi of B and then its inverse. So what is the value of phi A from this? It is a E dash identity. So this is a E dash raised to power minus 1. So inverse of identity is again identity. So E dash into E dash is equal to E dash. So it implies phi AB inverse. So it implies phi AB inverse is equal to E dash. So it implies AB inverse belongs to kernel of phi, then it implies kernel of phi is a subgroup of group G. So subgroup of group G. So remember this. So it is a subgroup of group G. Now second part, it is a normal subgroup. So to prove the normal subgroup, I will take one element from G and one element from kernel of phi. So I take A element from kernel of phi and G element from capital G, these values. Now, if A belongs to this kernel phi, so phi of A is equal to E dash, right? Now my aim is कि phi G inverse A G, it should be identity. Since phi is homomorphism, so this can be written as phi G inverse phi A into phi G. Now this value can be written as phi G raised to power minus 1 and this phi A by using this concept E dash into phi of A. So if identity multiply with any element, so that is equal to phi G raised to power minus 1 into phi of phi A E dash. So this is phi of g into phi of g. Now when we multiply, this value is equal to E dash. So they inverse, so they make is equal to E dash. So if phi of G inverse AG, so it implies phi of G inverse AG is equal to E dash for every A belongs to kernel phi and G belongs to capital G. So it implies G inverse AG belongs to kernel of phi for every A belongs to kernel of phi and G belongs to capital G. So it implies kernel of phi is a normal. So it satisfies two conditions. One is normal subgroup of of group G. So these are the properties of homomorphism. So these are basic property of the homomorphism. Now next result is if kernel of F, if homomorphism, next result a homomorphism. This is a homomorphism. So phi mapping from G to G dash, this mapping, and this mapping is a monomorphism. Monomorphism is 1 1. So this mapping is monomorphism if and only if kernel of phi consisting only identity element. So this is identity of G. So it consists only identity of this set. So this group. Now to prove the result, so this is, so prove this theorem. So this is a theorem number 2, this values. Now, so it has two part. For first I take let phi from G to G dash, where G and G dash are multiplicative group, is a monomorphism. Is monomorphism. Monomorphism. It means it is a homomorphism as well as 1 1. Now, I want to prove this result. Kernel phi consisting only identity element. So I take journal X arbitrary element from kernel of phi. Let X belongs to phi be some arbitrary element. So it implies phi of X is equal to E dash. So this value phi of X is equal to E dash. If phi of X is equal to E dash, this values, if phi of X equal to E dash, so since phi is homomorphism, so E dash can be written as phi E by property of homomorphism. So it means phi X which is equal to phi of E, this value. Now again, since phi is 1 1, so if phi is 1 1, then phi X equal to phi E, it implies X equal to identity. So it means any vector, any element from a kernel of a phi is identity. So it means kernel of phi consisting only one element, which is called a identity. So it is my first part. Now second part, conversely. Now conversely. So in the converse part, what is given? Given are two things. Number one, it is a homomorphism. So number one, phi from G to G dash be a homomorphism and kernel of phi consisting only identity element E dash, so kernel of phi consisting only one element, E element, because it is a part of G, so this is a E element, so not E dash. So remember, it is a E element, right? So also check in the previous part. So this is a E element. Now this, to prove what we want to show, that this phi is 1 1. So how we will prove 1 1 mapping? So let phi of A is equal to phi of B. So to prove 1 1, let phi of A which is equal to phi of B, right? This can be written as phi A, phi B inverse, this is inverse, is equal to E dash, means identity of G dash. Now since phi is a homomorphism, so it implies phi A, and this can be written as phi of B inverse, this value. So this is equal to E dash. Now it implies, since phi is homomorphism, so phi of AB inverse is equal to E dash. So if the image of any element is equal to identity, so that element belongs to kernel of phi. So what is kernel of phi? It consisting only identity element. So it implies AB inverse is equal to identity. So if AB inverse equal to identity, so it implies which values? So which is equal to A is equal to B. So what we get? We get phi is 1 1. If phi is 1 1, also it is homomorphism. So phi is monomorphism. Monomorphism. So phi is monomorphism. So which prove the result of this theorem. Now after that, this is our first result. This is our second result. Now after that, if we have an example, let G be a group. Let G be a group. So we already, I think, proved this example. So if G be a group and F is mapping from G to G, F is mapping from G to G, such that F of A, which is equal to A inverse for every A belongs to G. Now I change the name of mapping from phi to f. Why? Because I want to show that you should know the method. Don't memorize the name of the function या mapping. So to prove, show that G is abelian. G is abelian. So what is F? So this such that F from this is a homomorphism. So if mapping F is a homomorphism, then prove that G is abelian. So remember this result. If it is this mapping is a homomorphism, then prove that it is a abelian. Now, to prove the abelian, I take two elements A, B belongs to G. And my aim is to prove that AB is equal to BA. So I take AB, these values. Now what is AB? A is equal to A inverse raised to power inverse and B inverse raised to power inverse, which is equal to. Using this concept, so this will become f of A inverse into f of B inverse. So what is f? F is a homomorphism. So this is a inverse into B inverse. So this value is equal to, now by using reversal law, so this is a bracket B A inverse. By using reversal law, AB inverse is equal to B inverse A inverse. So this is equal to f of BA inverse. Again using the definition, so this will become BA for every AB belongs to G. So if F is a homomorphism, then G is a abelian. So what we get? We get this group G is a abelian group. So in this way, we can prove that, so this is a abelian group. Now, after that, the next result is, we define if a mapping F from G to G dash, if this mapping is an isomorphism. So it means it is a 1-1 onto and homomorphism. So three part. So this can be written as G of this kind. This. It means G is isomorphic to G dash. So this is a relation. This relation means there exists a F mapping from G to G dash, which is a isomorphism. Means homomorphism 1-1 and onto. My aim is to prove this relation is a equivalence relation. My aim to prove the relation of isomorphism. So next theorem is the statement of the theorem. The relation of an isomorphism. So relation of isomorphism in the set of all groups in the set of all groups is an equivalence relation. Equivalence relation. So this is a equivalence relation. So proof of this theorem. So what is equivalence relation? Which satisfy three terms. Which are the three terms? So one term is reflexive. Second is it is a symmetry. Third is it is a transitive. So reflexive mean it is related to itself. Reflexive mean it is related to itself. Symmetry means A implies B, it implies B implies A. मतलब अगर A B ਨੂੰ 10 ਰੁਪਏ ਦੇ ਰਿਹਾ ਤਾਂ B ਵੀ A ਨੂੰ ਵਾਪਸ 10 ਰੁਪਏ ਦੇ ਰਿਹਾ. So this is called a symmetric relation. Transitive means A implies B, B implies C. Then it means A is implies C, या A is related to C. So this is a transitive property. अगर A ने B ਨੂੰ 10 ਦਿੱਤੇ ਤਾਂ B ਨੇ C ਨੂੰ 10 ਰੁਪਏ ਦਿੱਤੇ ਤਾਂ A ਜਿਹੜਾ ਉਹ ਬੇਸਿਕਲੀ C ਨੂੰ 10 ਰੁਪਏ ਦੇ ਰਿਹਾ. So that is related to this. So first property is reflexive. Reflexive. So first reflexive property, group is related to itself. Group is related to itself. It is a reflexive property. Now I take G be a sum group. So I take G be a sum group and F is sum mapping from G to G, which is defined by F of X, which is equal to X for every X belongs to G. It means it is an identity mapping. Now, to prove that it is a homomorphism, 1, 1 and on 2. So, I want to show that it is a homomorphism. So, let X and Y belongs to G. So, it implies F of X, Y by definition this is equal to X, Y. Again by definition it is equal to Fx and Fy for every X, Y belongs to G. So it means this map F from G to G, this is a homomorphism. So first part is homomorphism. Now second is 1, 1. So to prove 1, 1, let Fx which is equal to Fy. So what it implies? It implies X equal to Y. Why? Because its value is X and its value is Y. So it means this mapping F is 1, 1. So this is a second property. Now third property is onto. So clearly this map is onto because for every element X there exists a element this X. So for every image it has a pre-image. So clearly it is a onto. So clearly F is onto. So it means F is 1, 1 onto and homomorphism. So it implies F from G to G, it is a homomorphism. 1 1 and on to. So it means this is a isomorphism. If isomorphism, then G is isomorphic to itself. So it proves the reflexive property. Now, second is symmetry property. Third is transitive. So second is symmetry property. Symmetry property. So what is symmetry property? Let G1 and G2 be two groups such that G1 is isomorphic to G2. To prove the symmetry property, I want to show that G2 is isomorphic to G1. Now, if G1 is isomorphic to G2, so by definition there exists a mapping F from G1 to G2, so which is a homomorphism. Yeah, simply is an isomorphism. Isomorphism means homomorphism 1 1 and on to. Now, if it is a isomorphism, means homomorphism 1 1 and on to. So since it is a 1 1 and on to, so since F from G1 to G2, it is 1 1 and on to, so it inverse exists. So it implies there exists F inverse from G2 to G1, right? So it inverse exists, which is 1 1 and on to, which is again, so it inverse exists, which is 1 1 and on to, 1 1 and on to. So it inverse exists, so it is 1 1 and on to. Now to prove the homomorphism, so I take two element, let x dash and y dash, so these are two elements from G2. So since this mapping F from G1 to G2 is onto, so it means every element has pre-image. So there exists x, y belongs to G1 such that x dash is equal to f of x and y dash is equal to f of y. So this is by definition of onto. So it means f of x is equal to this values. Now f inverse x dash is equal to x. So to prove it is a homomorphism, f inverse x dash into y dash, this values, f inverse into x dash into y dash. So this can be written as f inverse bracket, this values, substitute the value of x dash. So this is fx and it is a fy. Now since f is a homomorphism, so by using the property of homomorphism, f inverse bracket, so this is f of xy. Now f inverse of f is equal to identity. So this is identity of xy, so which is equal to x into y. Now substitute the value of x and y from this. X is f inverse x dash into f inverse into y dash. So f inverse is a homomorphism. So it is 1 1 onto as well as homomorphism. So it implies this f inverse from G2 to G1. So this is a homomorphism, 1 1 and 1 1 and onto. So it implies G2 which is isomorphic to G1. So it proves the symmetry property. Now third is transitive. So to prove the transitive property, now I take three group property. So I take three group. So let G1, G2 and G3 be three groups such that G1 isomorphic to G2 and G2 is isomorphic to G3. Now my aim is to prove that G1 is isomorphic to G3. So that is my aim. Now by definition, since it is isomorphic to this, so there exists a mapping F from G1 to G2 which is a homomorphism 1 1 and onto. Just simply we can say that is an isomorphism. So this is a isomorphism. Similarly, G2 is isomorphic to G3. So there exists G2 to G3. It is again isomorphism. So this is again isomorphism. Now, what we get, so just see the picture. So we have three group. So this is G1, this is G2 and this is a G3, right? Now from G1 to G2 there is map F and from G2 is G3 there is map G and this is isomorphism and this is again isomorphism. Now this is homomorphism, 1 1 and onto. And same here, homomorphism, 1 1 and on to, right? Now I define a composite map. That map is from G to G3, this map. And composite map is G of F. So this is F map, this is G map. So I define G of F, which is a composite map. Now if F is 1 1 on 2, G is 1 1 on 2, then composite map is also 1 1 on 2. So define composite map G of F from G1 to G2. So this is a again 1 1 on 2. So since F is 1 1 on 2, G is 1 1 on 2, so it implies define a composite map. Composite map. Now since F is 1 1 on 2, G is 1 1 on 2, so it implies G of F is 1 1 and on 2. So what is the remaining part? Remaining part is only homomorphism. Now to prove the homomorphism, let two elements X and Y, it belongs to G1, right? So this is the three part, G1, G2, G3. So here I take X and Y. So this is F, this is G, right? This value. Now, to prove the homomorphism, G of F of XY can be written as G bracket F of XY. Now what is F? F is homomorphism. So this can be written as this values, and this is Fx and Fy, this values. Here I am using F is a homomorphism. Now again G is homomorphism, then it implies G of Fx and G of Fy. So what I get? I get G of F of X, G of F of Y. So this is property of homomorphism. Now this map G of F from G1 to G3. So this map is homomorphism 1 1 and on 2. So it is an isomorphism. If it is isomorphism, so it implies this G1, which is isomorphic to G3, right? So just display this number. So this G1, which is isomorphic to G3. So it means this relation is an equivalence relation. So relation of isomorphism is an equivalence relation. So in the next lecture, we will discuss very important theorem which is called fundamental theorem of homomorphism.